Okay. Okay, Lulu. I think that what you're confusing is the difference between how much energy a substance has before and after a reaction and the energy associated with bonds breaking and forming. So we're going to go back to the lemonade stand example and just see if we can make it work. So let's say there's a kid who has $150. He has a lemonade stand. It's a success. At the end of the lemonade stand, he has $200. Okay? And we're going to ignore what happens in between. Okay? Conversely, there's this other kid who puts his lemonade stand on a cul-de-sac, and it's a big bust. Okay? And he loses a bunch of money. And we're going to ignore the middle steps there. Okay? For these two examples, delta H for this one is positive because this kid has more money at the end than they had at the beginning. So the kid has gained money. And the amount of money that he's gained is comparing his initial bank balance, which was $150, to his end, which was $200. But what matters is the change. In chemistry, you can also have something gain money, so to speak, gain energy over the course of a reaction. We never, in chemistry, the difference between this example and chemistry is in chemistry, we don't usually talk about the, absolute amount of enthalpy that something has. We don't talk about how much H it has. We talk about the change in H. But if we were to talk about the amount of H it has, in this case, it had 150 initially, it had 200 later. In contrast with this one, the difference was, this isn't really to scale, negative delta H was 100 minus 50 was negative 50. Okay, dollars, but we could say kilojoules. Okay? So this delta H is just that, comparing the amount of energy the reactants and the products have. So with endothermic, which of course is this one on the left, you have more energy at the end than you had at the beginning. The products have more energy than the reactants. Which is why the system had to absorb energy to go from reactants to products. And that's why delta H is positive. Final minus initial is a positive value. Okay, whereas in this case, the products have less energy. Okay, and this is completely ignoring the bonds, the energy required to make and break the bonds. But I hope that this part makes sense. This one on the left is endothermic because energy is being absorbed by the system. So how does that relate to bonds then? That we can go back to the lemonade stand example for a minute. The lemonade stand analogy breaks apart a little bit, but I think it's still useful. So let's look at this kid on the left. Let's say that in order to buy all of his lemonade supplies, he had to spend $20. So there was a moment, and I think you know that in chemistry this graph looks like this, but we're going to show it how it would be for lemonade stand. So when the kid buys his lemonade ingredients, maybe his balance dips down to like 130 for a minute. Okay, but then let's say he sells the lemonade and makes $70. So that's why it goes back up to this. So what we have here is what he spent and what he earned. 1 second. And the difference between those is what determines whether or not he overall loses or makes money. Because over here you can say like, oh, let's say that this kid was sort of foolish and spent $70 on ingredients. Got down to 80 here, and then he only made $20. Whoops. So this kid, conversely, spent 70 and earned 20 for a total of, and this one spent, what did I say, spent 20 and earned 70. Okay, so if you want to break it down and look at the actual energy changes over the course of the process, you can see that this one on the left, less money had to be paid than what was earned, and therefore the overall impact was that he there was a gain of money to his system. Okay, if we were to look at this from the chemistry perspective, it's a little tiny bit different, because whereas this kid had to lose money to convert, like to first go from reactants to products. In chemistry, you first have to gain energy to go from reactants to products, because of course when you have reactants, they're bonds need to be broken in order for them to start to convert to products, and breaking bonds requires energy. That's why regardless of whether the reaction's endothermic or exothermic, you always first have to break bonds, which requires energy. Okay, so this first bit up to here is the energy required to break the reactant's bonds. And because you have to put energy into the system to do that, the system, which this bank balance is like the system's energy, the system has to gain energy to do that. Okay, and when you do that, then you get this much, and then the bonds and the products form, and the bonds and the products forming releases energy. So we'll say this is the energy released when bonds in products form. Okay, so the difference between this one on the left and this one on the right does dictate the magnitude of delta H. But it's not the same thing as these numbers over here. Okay, because you could imagine that this graph, if it went down further, and this was 350 and 400, delta H would still be the same, and these energies could still be the same. And you can also imagine that if this curve went up to here and back down, like the energy required to break the bonds in the reactants and the energy required when the bonds, or released when the bonds in the products formed, those would both be higher, but the difference could still be 50. So when a question says, like which has more energy, the reactants and the products, in endothermic, the products have more energy because it's higher up on the y-axis, okay? And if you're saying, well, which one releases, or what involves a greater change in energy, breaking the bonds in the reactants or releasing energy when the bonds in the products form, in order to go from down here to up here, this section must be greater than this section. So the amount of energy required will always be greater than the amount of energy released. And because of that, the system is taking energy in. More is required than is released. So there's an overall gain of energy, which is why you have this delta H being positive. The system is gaining energy. The products have more energy than the reactants. The system absorbed energy from the surroundings, which are colder. In contrast, you can look at over here. If we have this guy, a certain amount of energy is required to break the bonds in the reactants. So this is energy in to break bonds. So the system is gaining energy. However, in this case, there's more energy out when the bonds in the products form. Okay? So we'd say this is energy out when bonds in the products form. Okay, so in this case with exothermic, let's say energy released is greater than energy required, which makes sense. So overall, there's more energy out than energy in. Energy out is greater than energy in. Okay, conversely with endothermic, the energy released is less than the energy required. Maybe I should have written those the other way around just to match the graphs, but oh well. And the energy out for endothermic will be less than the energy in. Okay, you're not going to watch it if it's too long, so hopefully that helps a little bit. Let me know if you have more questions.